Last class we were discussing transmission line and deriving transmission line equations, that are the equations for voltage and current. And in this class we will go through the derivations for input impedance, reflection coefficient and standing wave ratio. So first we will move on to input impedance, which is a very important parameter of transmission line. So consider this figure. This shows a transmission line of length L starting from here to here. Here at this point Z will be equal to 0 and at the end point Z will be equal to L. So total L length transmission line, and in one end you have the generator and the other end you have the load. Voltage across the load is VL, current through the load is IL. So that is VL, IL and voltage across the load VL and the load impedance is ZL. Then coming to this end, the initial point at the generator Z equals 0. The voltage is taken as V0 and current is taken as I0. So we are taking 2 points, one end the generator end and the load end, and here it is Z equals 0 where voltage is V0 and current is I0. Similarly at Z is equal to L, that is at the load end, V can be taken as VL and I can be taken as IL. Okay, you can take like this. And the two parameters, gamma is the propagation constant and Z0 is characteristic impedance. So you have to know it's all different. Z0 is the characteristic impedance of the transmission line. It is characteristic impedance. And we are going to derive the input impedance, that is given by Zin, and ZL, that is load impedance. And we can calculate the input impedance at any point of the line, and Zin is equal to VSZ divided by ISZ, and this is valid at any point of the transmission line. This is at any point of the transmission line you can calculate the input impedance. Okay, so if you are calculating at this point, say this length be L dash, then what will be this length? This will be total length is L minus L dash. So at any point you can calculate the Zin. You have to give this value correspondingly. So at any point of the transmission line you can calculate the input impedance with the equation voltage by current corresponding to that point. You will get the input impedance at that point. And coming to the basic, we will start the derivation for input impedance. So this is the basic equation for voltage and current. VSZ is V0 plus e raised to minus gamma Z plus V0 minus e raised to gamma Z. This is the negative travelling part or the reflecting part of the wave. Similarly current also, please note that there is a negative sign for the second term. V0 plus by Z0 e raised to minus gamma Z minus V0 minus by Z0 e raised to gamma Z. These are the voltage and current equations, and the last class we discussed and derived all these equations. So let's proceed to the derivation of input impedance. Let's take Zin is VSZ divided by ISZ, and equations are VSZ is equal to V0 plus e raised to minus gamma Z plus V0 minus e raised to gamma Z. This is equation 1. And what about ISZ? ISZ is equal to V0 plus by Z0 e raised to minus gamma Z minus V0 minus by Z0 e raised to gamma Z. This is equation 2. And at Z is equal to 0, at Z is equal to 0, you get, we assume the voltage to be V0 and current to be I0. So on substituting Z is equal to 0, you will get V0 is equal to V0 plus V0 minus. Why? Because e raised to gamma Z term and e raised to minus gamma Z term will be reduced to 1 as Z is equal to 0. E raised to 0 is 1. So this will be from equation 1, when you substitute Z is equal to 0, you get V0. VSZ at Z equals 0 is V0. So V0 equals V0 plus V0 minus. Equation 3. And when you substitute this Z equals 0 corresponding to equation 2, what you will be getting? Voltage at Z is equal to, current at Z is equal to 0 is I naught, will be equal to V0 plus by Z naught minus V0 minus by Z naught. This can be written as I naught Z naught is equal to V0 plus minus V0 minus. Let this be equation 4. Now you are deriving the voltage and current equation at Z is equal to L. Again at Z is equal to L, voltage is VL and current is IL. Again substituting in equation 1 and 2, you get VL is equal to V0 plus e raised to minus gamma L plus V0 minus e raised to gamma L. And IL is equal to V0 plus e raised to minus gamma L minus V0 minus e raised to gamma L by Z naught. That is IL Z naught is equal to V0 plus e raised to minus gamma L minus V0 minus e raised to gamma L. So you have these two equations, and now we are trying to calculate V0 plus and V0 minus in terms of VL, IL and Z naught. So let this be equation 5 and let this be equation 6. From these two we will get, you can add 5 and 6, you will be getting, on adding 5 and 6 you will be getting V0 plus is equal to half into VL plus IL Z naught into e raised to gamma L. Let this be equation 7. Similarly, you will be getting V0 minus as half into VL minus IL Z naught into e raised to minus gamma L. Let this be equation 8. So I am not explaining each and every step because it will be more confusing. You can just check equation 5 and 6. Equation 5 and 6, when you add, what you will be getting? When you add, these two terms will get cancelled. So 2V0 plus e raised to minus gamma L will be equal to VL plus IL Z naught. From that you will get V0 plus. And when you subtract 5 and equation 6, that is 5 minus 6, what you will be getting? VL minus IL Z naught is equal to, second term you will be getting 2V0 minus e raised to gamma L. From that you can calculate V0 minus. So you what you did after getting 5 and 6, you do 5 plus 6, you will be getting 7th equation, and 5 minus 6 you getting equation 8. Now you have equations for V0 plus and V0 minus in terms of VL, IL and Z naught. Now we will go to the basic equation for input impedance, that is Zin. Zin is equal to VSZ by ISZ corresponding to a particular point in the transmission line. So this can be calculated for any point, but at the generator, Zin. So total input impedance can be taken from the generator. When we are looking from the generator, Zin is equal to voltage at Z equals 0 divided by current at Z equals 0. That is V0 by I0. You have the equation for V0 and I0. What is the equation? Here you have V0 and I0. From equations 3 and 4 you are getting V0 plus V0 minus divided by I0 you will get from equation 4, that is V0 plus minus V0 minus divided by Z naught. This will be Z naught into V0 plus V0 minus divided by V0 plus minus V0 minus. You are getting the input impedance equation. Now you are going to substitute for V0 plus and V0 minus from equation 7 and 8. So you are substituting, let this be equation 9. You are substituting 7 and 8 in equation 9. You will be getting Z in is equal to Z0 into V0 plus plus V0 minus. And this 1 by 2 is common in all the term, both in numerator and numerator, the same term. So half you can cancel and you can write VL plus IL Z0 into e raised to gamma L plus VL minus IL Z0 into e raised to minus gamma L divided by VL plus IL Z0 into e raised to gamma L minus VL minus IL Z0 into e raised to minus gamma L. Get this equation. Next step is you substitute VL is equal to IL ZL. Okay, voltage across the load is current through the load IL and load impedance. So VL can be substituted as IL ZL. And in one more thing I am doing in the same step, IL, when you substitute IL for this term, you can see that there is an IL coming throughout. So you are cutting off IL also. So first step is I am substituting VL is equal to IL ZL, and in the next step I am cutting out IL because it is common in each and every term. So you can write it as Z0 is equal to IL ZL. IL get cancelled, so it will be ZL plus Z0 into e raised to gamma L plus ZL minus Z0 into e raised to minus gamma L divided by ZL plus Z0 into e raised to gamma L minus ZL minus Z0 into e raised to minus gamma L. You will be getting like this. Now you are taking ZL terms common. So you will be getting Z in is equal to Z0 into ZL into e raised to gamma L plus e raised to minus gamma L plus Z0 into e raised to gamma L minus e raised to minus gamma L divided by ZL into e raised to gamma L minus e raised to minus gamma L plus Z0 into e raised to gamma L plus e raised to minus gamma L. You will be getting like this. But one thing you should know is e raised to gamma L plus e raised to minus gamma L is 2 cos h gamma L. Similarly, e raised to gamma L minus e raised to gamma minus gamma L is 2 sin h gamma L. So based on that, substituting, you will be getting Z0 into ZL into e raised to gamma L plus e raised to minus gamma L is 2 cos h gamma L plus Z0 into 2 sin h gamma L divided by ZL into e raised to gamma L minus e raised to minus gamma L is 2 sin h gamma L plus Z0 into 2 cos h gamma L. So you will be getting the equation like this. Now the final step, you are dividing the equation throughout with sin h gamma L. You are dividing throughout with sin h gamma L. You will be getting Z in is equal to Z0 into ZL. 2 is common, it's throughout, you can divide with 2. Z0 is ZL into, when you divide with 2 cos h gamma L, what will happen? This term only exists, and in next case it will be Z0 tan h gamma L divided by ZL tan h gamma L plus Z0. Be getting like this. So Z in is equal to Z0 into ZL plus Z0 tan h gamma L divided by Z0 plus ZL tan h gamma L. This is the final equation for input impedance of a transmission line. The equation for input impedance of a transmission line. Okay, so this L represents the length of the transmission line. Length of transmission line. Z in, that is input impedance. Z0, what is Z0? Z0 is characteristic impedance. ZL is load impedance. Gamma stands for propagation constant. So this is a very important equation. It's the equation for input impedance. One more thing, if you are considering a lossless line, okay, if you are considering a lossless line means alpha is equal to 0. Then gamma, alpha plus j beta will be reduced to j beta. So if it is a lossless line, gamma will be j beta. So what you can do, you can substitute for, instead of tan h gamma L, you can substitute tan h j beta L. This will be equivalent to j tan beta L. So in case of a lossless line, Zin is equal to, substituting in our final equation, Z0 into ZL plus j Z0 tan beta L divided by Z0 plus j ZL tan beta L. This is the equation for input impedance in case of lossless line. So this is a general equation for input impedance, and in case of lossless line, the equation for input impedance is this. So it's a very important derivation, and final equation is also very important. For exam, you have to learn this complete derivation for input impedance. So these are the final equations. Input impedance, the equation is like this: Z0 into ZL plus Z0 tan h gamma L divided by Z0 plus ZL tan h gamma L. You have this bracket. Okay. And in case of lossless line, gamma is j beta. So tan h gamma L will be reduced to tan h j beta L and j tan beta L, and this is a reduced equation in case of lossless line. General case is the first equation, and in case of lossless line, this is the equation. And next is voltage reflection coefficient. The equation for reflection coefficient is, the definition itself states that it is the ratio of reflected voltage wave to that of the incident wave. The equations are, VSZ is given by V0 plus e raised to minus gamma L plus V0 minus e raised to gamma L. So this is the equation. So from this, if you want to calculate the equation for reflection coefficient, it will be voltage reflection coefficient will divide by V0 minus e raised to gamma L divided by V0 plus e raised to minus gamma L. This can be written as V0 minus divided by V0 plus e raised to 2 gamma, e raised to 2 into gamma into L. Okay, this is the equation. And from the last derivation, we know the equations for V0 minus and V0 plus. You can directly substitute here. What you will be getting, know the equations. The equation was V0 minus is VL minus IL Z0 into e raised to minus gamma L divided by VL plus IL Z0 into e raised to gamma L. This is the equation, and there is a 1 by 2 term that will be getting cancelled. So this was the equation, and this into e raised to, here you have, when you divided, you got e raised to 2 gamma L. So what will happen here? In reflection coefficient, you get VL minus IL Z0 divided by VL plus IL Z0 into e raised to minus 2 gamma L into e raised to 2 gamma L. So both these will be cancelled and you will be getting VL minus IL Z naught divided by VL plus IL Z naught. Again you substitute VL is equal to IL ZL. IL ZL minus IL Z naught divided by IL ZL plus IL Z naught. So what you will be getting? ZL minus Z naught divided by ZL plus Z naught. So you got the reflection coefficient as ZL minus Z naught divided by ZL plus Z naught. This is a very important equation, reflection coefficient of a transmission line. It is given by ZL minus Z naught divided by ZL plus Z naught, where ZL it is load impedance and Z naught is characteristic impedance. Characteristic impedance. We derive the equation. We derive the equation for input impedance and reflection coefficient. Now let's check the equation for standing wave ratio. Standing wave ratio or SWR or S. The equation for standing wave ratio or S is given by ratio of maximum voltage to minimum voltage, Vmax by Vmin. This is also equal to Imax, maximum current to minimum current. So standing wave ratio, it's the ratio of maximum voltage to minimum voltage or maximum current to minimum current. And derivation I am not discussing now. The final equation is 1 plus reflection coefficient divided by 1 minus modulus of reflection coefficient. This equation is very important. It's the equation for standing wave ratio. 1 plus modulus of reflection coefficient divided by 1 minus modulus of reflection coefficient. And you might be remembering the equation for reflection coefficient we discussed in earlier, that is ZL minus Z naught divided by ZL plus Z naught. So this is the equation for reflection coefficient, and equation for standing wave ratio or S is 1 plus modulus reflection coefficient divided by 1 minus modulus of reflection coefficient. And now we discuss the equation for input impedance, and let's check the equation or the maximum value of input impedance. The maximum value of Zin. Maximum value of Zin is given by Vmax divided by I minimum. That is, maximum value of input impedance is the ratio of maximum voltage to minimum current, and minimum current occurs corresponding to minimum voltage. So it will be Vmin by Z0. This will be equal to Z0 into Vmax divided by Vmin. So from this you can write Vmax by Vmin, you know that ratio is S. So it will be S Z0. So the maximum value of input impedance will be S into Z0, where S is standing wave ratio and Z0 is characteristic impedance. Now let's check what is the minimum value for input impedance. Z in minimum is given by Vmin divided by numerator should be minimum and denominator should be maximum, that is Vmin by Imax. Again Imax corresponds to maximum amplitude of voltage, so Vmax by Z0. It will be Z0 into Vmin divided by Vmax. Again you know that Vmax by Vmin is S, so it will be Z0 by S. So from these two you can derive the equation as Zin max into Zin minimum. Maximum impedance into minimum impedance will be, it will be S Z0 into Z0 by S. It will be Z0 square. This is an important equation. You should remember that also. Zin max into Zin minimum. The product of minimum and maximum value will be equal to Z0 square. Here Z0 is characteristic impedance of the transmission line. Characteristic impedance of the transmission line. Now let's consider the three special cases, that is, one is a short circuited line. Short circuited line. In case of short circuited line, load impedance will be 0 because in the load it will be shorted. So the load impedance will be 0. So that's one case. In that case, what will be the equation for the input impedance? Input impedance corresponding to short circuited line. That will be the general equation for the input impedance of a lossless line is Z0 into ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L. This is the general equation for a lossless line, and we are considering a short circuited line. Short circuited line means ZL is equal to 0. You are substituting ZL is equal to 0. You are getting Z0 into J Z0 tan beta L divided by, again ZL is 0. So it's divided by Z0. So you will be getting J Z0 tan beta L. So this is an important equation. So input impedance corresponding to short circuit can be represented like this: ZSC. ZSC is equal to J Z0 tan beta L. J Z0 tan beta L. This is the equation for input impedance of a short circuited line. Next case, what is the reflection coefficient corresponding to short circuited? Here this is the equation. Again you are substituting ZL is 0. So what will happen? Minus Z0 divided by Z0, that is equal to minus 1. What about S corresponding to short circuited line? It will be 1 plus modulus of reflection coefficient is 1 divided by 1 minus 1, that is 1 by 0, or it will be infinity. So these are the three values you should remember corresponding to a short circuited line. When ZL is equal to 0, the impedance will be J Z0 tan beta L, reflection coefficient will be minus 1, and standing wave ratio will be infinity. Okay, this means that input impedance for a short circuited line will be completely reactive. It will be it is a pure reactance because it just have the imaginary part, no resistive part, no real value, no real component. So it is pure reactance. Zn is pure reactance in case of short circuited line. Now let's discuss the second case, which is open circuited line. In case of open circuited line, ZL is equal to, it is open, so ZL will be infinity. When ZL is infinity, what happens? Firstly, we will derive the input impedance. It will be, this is general equation we already wrote. So let's apply ZL is equal to infinity. So let's make ZL in the denominator. For that, you divide throughout numerator and denominator with ZL. So what will happen? Z0 into 1 plus J Z0 by ZL into tan beta L divided by Z0 by ZL plus J. ZL is there. So J tan beta L. Okay, so you are dividing throughout with ZL. So 1 J Z0 by ZL, again Z0 by ZL, and J tan beta. So whenever ZL value is infinity, 1 by ZL will be 0. So both these terms, ZL equal to infinity, both these terms will be 0 because 1 by infinity is 0. So this can be written as Z0 divided by J tan beta L. This will be, when you multiply numerator and denominator with j square is minus 1. So it will be minus j Z naught cot beta L. So this is the next equation you should remember, that is impedance corresponding to open circuit is minus j Z naught cot beta L. Now let's check the equations for reflection coefficient. Reflection coefficient is that OC is equal to ZL minus Z naught divided by ZL plus Z naught. Again you divide 1 minus Z naught by ZL divided by 1 plus Z naught by ZL. So here both these terms become 0 as ZL is infinity, so it will be 1. Similarly, S value will be 1 plus 1 divided by 1 minus 1. It will be infinity. So you get the values for open circuited line as reflection coefficient will be 1 and standing wave ratio will be infinity. So these are the two values you should remember. In short circuited line, reflection coefficient is minus 1, and in open circuited line, reflection coefficient is 1. In both cases, standing wave ratio will be equal to infinity. Now another thing you should learn is input impedance corresponding to short circuit into input impedance corresponding to open circuit. This is another important relation you should know. ZSC into ZOC will be, first value is, you can see here, it is J Z naught tan beta L. So it is J Z naught tan beta L into minus J Z naught cot beta L. What will happen? Tan beta L and cot beta L multiplying, it will be 1. Again J square minus 1 into minus 1, it is again 1, and what you will be getting is Z naught square. So this is another important equation you should know. Short circuited line impedance into open circuited case. If both these values are given in some problem, you can calculate characteristic impedance. So this is another important equation. ZSC into ZOC will be square of characteristic impedance. Now we will discuss the last and the third case, that is matched line. Matched line. Matched line is the particular case when ZL, the load impedance, is equal to characteristic impedance. This is the case. ZL is equal to Z naught. What will happen? Zin is equal to Z naught into ZL plus J Z naught tan beta L divided by Z naught plus J ZL tan beta L. This is the equation that we know. Okay. And when this happens, both these terms will be same because ZL and Z naught are equal. So both numerator and denominator is same, and it becomes equal to Z naught. So corresponding to a matched line, input impedance and load impedance both will be equal to Z naught, which is characteristic impedance. And what about reflection coefficient? It will be ZL minus Z naught divided by ZL plus Z naught. So it will be Z naught minus Z naught divided by Z naught plus Z naught. It will be 0. So there is absolutely no reflection. Reflection coefficient is 0. And what about S? 1 plus modulus of reflection coefficient divided by 1 minus modulus of reflection coefficient. It will be 1. Okay, so in case of matched line, reflection coefficient is 0 and S value is 1. That means in case of matched line, whole wave is transmitted. Whole wave is transmitted and there is no reflection. There is no reflection and the wave is completely transmitted in case of matched line. And this corresponds to which case? The maximum power transferring case. Maximum power is transferred in this case. Maximum power transfer is possible when a transmission line is matched to the load. Here ZL load impedance is equal to characteristic impedance. That means the line impedance is matched to load impedance. Corresponding to this case, maximum power is transferred. And it is proved like this. Reflection coefficient is 0 and S is 1. So absolutely no reflection and wave is completely transmitted. Input impedance will be equal to characteristic impedance in case of matched line. So learn the three cases. One is short circuited line, then open circuited line and matched line. All the three cases, the equation for Z in input impedance, reflection coefficient and standing wave ratio.